Alrighty, just give me a moment to hopefully get to the right place on the slides. Okay. All right, and let me just start a timer for myself so I know how I'm doing. Okay. All right, here we go. Here we go. Hopefully, you saw some of this during the break. So, Horndeski is a name we've talked a lot about in these lectures, and that comes from Gregor Horndeski, who is the physicist who actually wrote down this sort of uber general theory of gravity with an extra scalar field. And he did that in the 70s, long before dark energy was discovered. He was a student in sort of mathematical aspects of general relativity. And from what I've understood, it was kind of like an exercise set to him by his supervisor. But Horndeski then left physics a couple of years later and became an artist and makes these sort of really nice, colorful acrylic knife paintings. I've got some examples on the slide there, and you can see more on his website. He is aware that his theory is being used. He has been to a few conferences and things, so he has sort of got back in touch with the physics here. Okay, um, so what we're going to do in this talk is in this half of the talk is kind of putting it all together. We started doing that a little bit already with the things we were doing just before the break, right? We took our gravitational wave data, we derived a bound on this slightly sort of phenomenological parameter like alpha t and alpha m, but we were able to convert that result on that alpha t object back into something that had major implications for the structure of modified gravity theories that we were allowed to write down. Right, so that's pretty cool, right? That's the kind of interplay between data and theory that we really like to see. So this was the full Horndeski Lagrangian we had to start with. And now, after having demanded that gravitational waves travel at the speed of light, this is the reduced version we're left with. Sometimes gets called luminal Horndeski gravity because it is the subsector of Horndeski gravity in which gravitational waves travel at the speed of light. Okay, and it's still parameterized by three functions. K and G3 are still functions of a scalar field and its kinetic term. This object G4, the conformal coupling, is only a function of the scalar field. It can't have a dependence on X. So although it looks a lot simpler than what we started with, life still gets pretty messy working with this theory. Once you've taken all the derivatives of these objects, if you do cosmological perturbation theory, the equations still get pretty big pretty fast. So what happened sort of a few years after people started working on Horndeski gravity is that there was put forward a sensible sort of reparameterization of these three functions, K, G3, and G4, that applies to linear perturbation theory. So if we take this theory, we put in our FRW background and we do our linear theory around that, the objects that appear in the linear perturbation theory, we call them the alphas. And this is why I had alphas in the first half of the talk. So there are going to be four of these objects called the Horndeski alpha parameters, or at least there were four of them originally. Now, of course, post GW 170817, and for the action that we've got on the slide there, alpha t, which was the parameter describing the change to the speed of light, has been ruled out. And so we've got three left. So what these alpha parameters are doing, I will show you expressions for them in a minute, but quantitatively what they are doing is wherever there is a term appearing in the linear perturbation theory of Horndeski gravity that is not present in GR, it has one or more of these alphas sitting in it. So if you like, they are the coefficients of deviations from GR, but only at the linear level. That's really important. They are functions of redshift. That's what happens when you evaluate on the cosmological background and study perturbations around that. And that's much easier to work with than abstract functions of a scalar field and its kinetic term, right? And what's more is that these alpha parameters have kind of nice physical descriptions you can drape around them. So one of these we have met already, right? We met alpha m, which we said was the derivative of the G4 function with respect to the log of the scale factor. So basically a time derivative. And that tells you about that run rate of that effective Planck mass. Alpha B is called the braiding parameter, and it tells you about the a particular sort of kind of term that mixes the kinetic term of your scalar field and your metrics. Are they braided together? Are they interacting? And finally, there is one called alpha K, sometimes called the kineticity parameter, which is related to those non-trivial kinetic terms. So does our scalar field have a sort of standard kinetic term or something more exotic? Now, these objects can all be expressed in terms of those functions I had on the previous slide. So K, G3, G4, they are related to derivatives of those objects and linear combinations of those derivatives evaluated on the cosmological background. So I put the expressions on the slide here for completeness. In some sense, they're not particularly helpful or useful to look at. So it's easier just to think about these three alphas as things that we want to constrain to test this whole space of scalar tensor theories. And I will sometimes perhaps slip up and call them parameters. Obviously, they're not parameters, they are functions of redshift. Now, there's an extra simplification, which is going to come in from a very practical viewpoint. Alpha K, this kinetic term here, does not appear in the equations of linear perturbation theory on scales well below the cosmological horizon. And that is where most of our data is. Most of our telescopes are really looking at, relatively small scales in cosmological terms. It's only if you have something like a radio survey that really probes the very largest scales of the universe you can probe this guy. So we're going to leave it out for today. We will not talk about alpha K. Instead, what I want to do is try and build up a picture of how we constrain these remaining two functions, alpha B and alpha M. Okay, first of all, we have a restriction on this space of these functions coming from stability. So what is stability? So when we build a theory of gravity, there are certain restrictions we have to obey that ensure we are free from instabilities, so negative energy modes in our theory, for example. And so something that could happen is what's called a ghost instability. That's when the kinetic term of one of your degrees of freedom has the wrong sign. And that effectively allows the total energy of your theory to be unbounded from below. So you can create lots of ghosts by going to lower and lower energies. That's not allowed. Your theory is unstable. So to avoid that, you can work out how to ensure that the kinetic term of perturbations is always positive in Horndeski gravity, and it translates into a condition on those alpha parameters. I've written down a slightly simplified version of it here because I didn't want to have to introduce lots and lots of more notation, but it's something like this. It's like some algebraic combination of the alphas that has to be positive. Okay. So what we're going to do is we're going to start building ourselves this two-dimensional parameter space. And we're going to carry on using the kind of ansatz we had before. And I realize now, here's another typo on the slides. I've left off the omega lambda 0 on the denominator here. So sorry, that should be there. So we did that for alpha M. We're going to do something similar for alpha B. And what this does is it translates our sort of space of two functions into a space of two numbers that we can constrain. Okay, and so GR is the point where both of those constants of proportionality are zero, right? You set the alphas to zero, you get back to general relativity. Now, I was saying a moment ago, we have to avoid ghost instabilities, and there are certain conditions to do that. And generically, what they will do is they will rule out the sort of lower section of this plot. So what I'm doing here is I'm going to sort of make a sketch version of this plot, and then I want to show you the real data from a recent paper. So on the sketch version, bottom corner ruled out by instability. There's going to be another sector that's kind of ruled out, which is if this CM parameter is too large, and that's going to be ruled out by growth. So let's pick up an equation we had yesterday. We did a little bit of linear perturbation theory, and we arrived at this second order equation for dark matter density fluctuations, right? And we said you could solve this to find the growing mode of density perturbations. And if we had some modified gravity going on in the Poisson equation, it brought in this factor mu, which would be 1 in GR, different from 1 outside of GR, and that would change the rate of growth of perturbations. So you can work out what mu is in Horndeski gravity in terms of these alpha parameters. Again, you know, the expressions start to get a bit chunky, but here it is. M star here is just some mass scale I'm not going into. So what we actually measure, or something that can be measured by galaxy surveys, would be the growth rate, which we often call F, which we can define as the derivative of these dark matter density perturbations. Sorry for the slightly inconsistent use of subscripts here, with respect to time. But for various reasons, actually, it becomes easier to do a sort of logarithmic derivative of that quantity. And again, we use the log of the scale factor as a kind of time variable. So this is something that galaxy surveys are sensitive to. I don't know if Will might be discussing it in his lectures. But what we actually get out of a galaxy survey most naturally is a product of this growth rate F multiplied by a normalization factor, sigma 8, which is giving us the amplitude of perturbations in spheres of size 8 megaparsec in the universe. So this is just the quantity we can measure. And I'm showing it here again in Horndeski gravity. So our grey curve here is lambda CDM. We have some data points in black. I have forgotten to write on the slide which data points those are, but I think it's probably things like SDSS and BOSS. And you can see if we change alpha M and alpha B, now we're changing both of those parameters, we can get a sort of variety of different shapes of this curve. And clearly some of these models, like this pale blue one here, would be disfavored quite strongly by the data. So see, if we make alpha M larger and larger, sort of moving down the models here, we can sort of offset it with alpha B, but the general trend is if you make alpha M larger, you enhance this growth rate. And so that is what is going on when I sort of sketch on this plot that this upper region where CM is large, so alpha M is large, will be disfavored by growth when we use data from galaxy surveys. So these are sort of disfavored regions, but there are favored regions as well. So in these green triangles, I'm sketching in an approximate way. This is not a super accurate diagram on the slide right now. I'm sketching two regions where actually you'll see shortly that the data do allow us to have, well, the data are consistent with those regions. So why are there these sort of two directions? So this lower direction turns out to be a region in parameter space where there is no slip. So when we did a little bit of perturbation theory yesterday, we said that we have these two metric potentials, phi and psi, and in GR those two potentials are identically the same. And it's a very common feature of modified gravity models that they would no longer be the same. But if you sort of pick the right line in parameter space, then they are the same or very close to being the same. And that's that line down there. So if you move down this line, you're not the same as GR, but you're sort of one step closer to GR. You won't affect lensing observables very strongly. What's going on with this sort of upper green curve? This is an area in which, if you move in this direction, you have minimal impact on the integrated Sachs-Wolf ISW plateau of the cosmic microwave background. So let's talk about that just briefly. Of course, most of the CMB is really formed at high redshift. Most of that physics is set down at early times, and this has probably been covered in Eve's lectures. But there is one part of the CMB which is sort of sensitive to what happens in the late universe, and that is the largest angular scales. Because on those scales, the CMB photons are passing through sort of sizable features in the late time universe. So they're passing through gravitational potential wells. And in particular, that makes them sensitive to what those potentials are doing at late times. So particularly they probe the time derivative of those two potentials in this combination here. Now in lambda CDM, this sum of potentials is constant during the matter-dominated era, so the derivative is 0. And then at late times in the universe, as dark energy takes over, these potentials actually start to decay. And so this combination of phi dot plus psi dot is a negative quantity. But that can be changed in modified gravity, because remember, modified gravity changes how things grow with time. And so stuff might start to decay less, for example. So just to plot some of this, here is a temperature power spectrum of the CMB. It's got the Planck data on it, Planck 2015. The black curve is the lambda CDM fit to this data. And you can see there is a set of coloured curves here, which represent a family of Galilean models. That's just a particular subclass of Horndeski. We did mention them yesterday. So it's some modified gravity models. And you can see all of them don't touch the small angular scales of the CMB, but they do affect the large angular scales. Okay, and in particular, you can see this red curve is perhaps the most extreme one. So coming back to our diagram here, right, it's going to turn out that this particular direction in parameter space, and I haven't proven it, but is one where you don't impact that ISW plateau very much. Now, what we're going to do is bring in some data to make the sort of real version of this plot. So I'm going to use data from the Planck CMB temperatures power spectrum, which we just looked at. That will also have some modeling in it of the CMB lensing, right? So those CMB photons are lensed by small anisotropies at late times. And we're also going to bring in some galaxy clustering data. And those things will probe our space of alpha B and alpha M. We're also going to combine in this analysis data from baryon acoustic oscillations and supernovae. And both of those things constrain not the behavior of perturbations, but the sort of background expansion rate of the universe. So what I'm building up to here is a sort of excuse to show you one of the latest plots from the DESI survey. I'm not a part of DESI, so I'm just kind of picking this out of the literature, but it is the sort of latest, most recent bounds on these modified gravity parameters. So I thought it would be really nice to show you and sort of hopefully help you understand what's going on. So it is the parameter space we've got on the right there. And what do you see? First of all, in the dashed line, there is a constraint using just the baryonic acoustic oscillations from DESI, the supernovae, and the CMB data without lensing. So NL here means no lensing. And hopefully you can see it's got that sort of shape that I sketched over here, right? You're not allowed the bottom region, you're not allowed this sort of region over here, but there's definitely this sort of preference for this upper direction allowed by the CMB data. Then in the blue curve where it says plus FS, that means plus full shape. So that's bringing in galaxy clustering data from DESI. And you can see that kind of cuts off the top of that dashed curve. And that's doing exactly what we said it would in terms of that growth constraint, right? You're disfavoring large values of CM. And then in the orange, it brings in lensing of the CMB finally, and that produces a mild shift in these contours, nothing too substantial. Okay, so we get to a sort of bound here, right? This is our first real bound from EM data on these two quantities. Now, what's interesting is that you can see Cm is immediately consistent with zero, right? Should be the GR value. However, Cb, which is the coefficient of this braiding parameter here, actually looks like it has a sort of 2 sigma preference for being something away from zero, so a deviation from GR. It's too early to tell, and I'm sure there will be a further analysis from Desi down the road. But I'm going to try and explain why I don't think we should get too excited about that constraint right now. Because there is another piece of information that hasn't been kind of folded into this analysis right now. And that is something called the ISW galaxy cross correlation. So we talked about the ISW plateau of the CMB a few minutes ago, and we said it probes the sum of the time derivatives of those metric potentials. But actually, if you just use the CMB data, that's not sensitive to the sign of this quantity, because the CMB temperature power spectrum is like temperature fluctuations squared. So it kind of probes that quantity squared, and therefore it doesn't know if that quantity is positive or negative. However, there's another observable you can form, which is a cross correlation between the CMB, particularly that ISW plateau, and your galaxy survey. So you can think of it as kind of overlaying one copy of your CMB and your galaxy survey and computing some kind of overlap integral, if you like, between those two objects. So I've sort of sketched it probes in some sense the potentials multiplied by, this is your fluctuations in your galaxy distribution. And that thing does have sensitivity to the sign of the sum of those metric potentials. So here are those potentials in the same Galilean models we had earlier. So you're seeing the sum of phi and psi, what we identified yesterday as the lensing potential. And you're seeing it as a function of redshift. In some of my plots, time flows left to right. In this one, it flows right to left. So low redshift is at the left here. And in black, sorry, let me click ahead so we get the legend here. In black, we've got the prediction in lambda CDM, where we said that sum of potentials decays at late times. And in these colored curves, we've got those Galilean models. And you can see that they're doing a whole range of different things. So some of them are still ultimately decaying, but after they've increased a bit. And actually, there's a red curve here, which curves upwards. So in this particular model, which is called the cubic Galilean, the lensing potential actually increases with time as the universe evolves. In grey here is just marking the sort of region of a particular galaxy survey called WISE that was used in this paper that I'm taking the plots from to do this analysis and to build this cross correlation. Now on the right-hand panel here, we're plotting actually that cross correlation itself. So it's a fairly sort of boring looking curve, if I'm totally honest, right? So again, lambda CDM in black here, this is that kind of overlap object. And you can see the data points pretty well agreeing more or less with the lambda CDM value, at least at large scales. And we can see our other Galilean models. And most of them, particularly these solid ones, stay fairly close to the data. But again, some of them actually change the sign of this cross correlation. That's what we've picked up now, is the ability to distinguish the positive value in lambda CDM from the negative values in modified gravity. And in particular, this red curve here, the cubic Galilean, is actually ruled out now. Most people would consider it ruled out because of this measurement. And in fact, this particular paper, right? You cannot get the sign of this quantity correct in your modified gravity model in the cubic Galilean. So we're sort of laying down, if you like, all these different traps for modified gravity, right? We have to try and find all the ways it can break lambda CDM and then go look for data in those places. Okay, so what does this do to our sort of parameter space that we were sketching here? So this ISW galaxy cross correlation, what it tends to do is it tends to disfavor large values of this CB parameter. Okay, so if you go too far over here, the CMB lensing potential grows instead of decaying. And so I'm going to compare this sketch to a results plot from a different paper. So this is not the latest DESI paper, but actually a slightly older paper, or just a year older, in which the authors did a sort of similar analysis. So they're using Planck data, that's P18. And then they're bringing in that ISW galaxy cross data in orange. They've got some galaxy clustering data in the pink, and in the sort of dark purple is where they combine everything together. And so the yellow and the pink curves are kind of what we had before. There's that slight shift away from the zero value of CB. But if you bring in that ISW galaxy cross correlation, it seems to sort of shunt the curve back towards being around the 0 point. So this is purely my personal speculation in some sense, but I think probably if we see an analysis in future that does this cross correlation, we might see that kind of preference in the DESI paper for modified gravity to go away. This is just quantifying that in numbers. So here are the bounds that we had in the DESI analysis, where CB is completely consistent with, CM is consistent with 0. CB actually seems to be different from 0 if we take 0.33 away from 0.92. But in this other analysis, we see that both of them are consistent with 0. So this is the kind of game we play trying to pin down these modified gravity theories. Now, everything I have said so far in this lecture has been about linear scales, right? We've been using these alpha parameters, which are the kind of mapping of Horndeski gravity onto linear scales. Of course, there is data beyond the linear regime. And so to think about that, the sort of place to visualize that is the matter power spectrum, which I'm sure plenty of you will have met before. But its formal definition is given here on the slide. So the matter power spectrum is the object pk sitting in here. And it is the sort of statistical average of your two density fluctuations in Fourier space as a function of Fourier wave number k. So think of it as density fluctuations squared as a function of distance. And here is an example of a theoretical matter power spectrum. So because we're in Fourier space, we've got large scales at the left, we've got small scales at the right. And of course, because it's me lecturing just for fun, I had to have a modified gravity model on there. So you have in grey, you have the prediction of linear theory. And then in blue, you have the prediction of general relativity if you include nonlinear corrections which affect the small scales. And the other coloured curves, the kind of pinky ones, are F of R gravity models. Okay. So we've got the linear regime over here on the largest scales. Then we could say there's a sort of quasi-linear regime in which you need some really advanced perturbation theory techniques to make progress. And then on the smaller scales, you really are in a nonlinear regime, and we're going to need to do something else to model what modified gravity does to the power spectrum over here. So good. This is the regime we've been in cosmological perturbation theory. Now, this sort of relates to a question I saw someone asked on Slack the other day. People did ask about whether there's a sort of streamlined way to work with Horndeski gravity and compute all of the equations of linear perturbation theory in that modified gravity model. And the answer is yes, there is. So let's talk just briefly about tools for doing those computations in modified gravity in linear theory. So what you want is a tool called an Einstein-Boltzmann solver, right, which is a code which solves the sort of full set of coupled differential equations. And we've seen some of those equations today and in the previous yesterday's talk, but it's the equations describing the relationship and the evolution of your gravitational metric fluctuations, your density perturbations in all your species, so not just dark matter, but also radiation and neutrinos, baryons. And for some of those species, like neutrinos, you have to solve like a full Boltzmann hierarchy for the modes of their distribution. Hence the name Einstein-Boltzmann solver, because it kind of solves the Einstein equations and the Boltzmann equations. And this tool is your fast way to compute all of the observables we've been speaking about so far. So the linear large-scale matter power spectrum, the CMB temperature power spectrum, including that ISW plateau, and also lensing potentials, etc. And so Einstein-Boltzmann solvers have existed for quite some time in general relativity, but I wanted to sort of advertise, in case it's useful for some of you in your research, that there are sets of these Einstein-Boltzmann solvers that have been adapted to work in modified gravity theories. In particular, there is a code called high class, which stands for Horndeski in class. So that is the kind of tool that was sort of being sort of postulated on Slack. It will do all this perturbation theory in the language of the Horndeski functions we've been talking about. There's something called EFT-CAM, which uses an equivalent formalism. So you won't recognize the objects we've explored today, but there are equivalent versions where EFT, of course, is effective field theory. So it's really representing the effective field theory of dark energy formalism in CAM. Then there are a couple of others, and I won't go into the details of all of these. I haven't given links here, but you could go and Google any one of these names and come across these codes. Of course, if it was a sort of competition for cuteness of the logo, my money would be on Mochi class. Okay, so we know how to do stuff in the linear regime. However, most of the sort of frontier data from the galaxy surveys that you might have been hearing about this week, so DESI, Euclid, Vera Rubin, etc., Roman, most of that frontier data is really in that sort of quasi-linear to non-linear regime. And even in lambda-CDM, modeling those regimes is pretty tough, and you generally need n-body simulations. And that's true in modified gravity as well. So what you're going to need to do is take an n-body simulation and actually change it to operate with modified gravitational forces. And of course, at these very small scales, we're seeing quite substantial changes to gravity. And sort of, extrapolating wildly, you might well ask the question, isn't this going to change gravity in the solar system? Right? We said we didn't want to do that. We just wanted to change the large scales of the universe. But what I'm plotting here is that there's just more and more changes going on as we get to smaller and smaller objects. So this is why we need something like screening, which I've referred to a few times a little bit throughout the lecture. So what is screening? Screening is a set of properties that belong to modified gravity theories, some of them, in which non-linearities of the scalar field, usually it's a scalar field, act to suppress deviations from GR in certain environments. Now, not every modified gravity theory has a screening mechanism, but it is clearly a desirable feature. And so people have deliberately sort of tried to build models that have screening mechanisms because it helps you stay close to the data, right? If I tell you there's really tight bounds on deviations from GR in the solar system, your theory can't come along and predict that the moon is going to fall into the Earth, right? So these screening theories, there are a sort of few major classes of them known. And in particular, there's three big ones that get talked about a lot, which have the names chameleon, camouflage, and Weinstein screening. Now, I made the call not to go through all of these kind of in detail in the lectures because it does require a lot of derivations. It's kind of better done on a board. So at least chameleon screening is worked out in like full gory detail in my lecture notes. So I do encourage you to go look that up. But qualitatively, what's the sort of difference between these screening mechanisms? So in chameleon screening theories, this nonlinearity that suppresses all the funky modified gravity stuff activates when the gravitational potential is large. So it exceeds some threshold value I'll just call lambda. And this pops up in things like F of R gravity, which we met yesterday. In camouflage theories, screening activates when the first derivative of the potential is large. So that happens in, not surprisingly, the theory called camouflage. There's also a theory called DBI, Dirac-Born-Infeld. We haven't talked about it today, but it's another brain world model like DGP, and that activates camouflage. And then Weinstein screening, you've probably seen the pattern, activates when the second derivative of the metric potential is exceeding some value. And that's what happens in all of these Galilean models I've been speaking about. DGP gravity we saw yesterday. Just as another example, there's something called kinetic gravity braiding. So that is how, in some sense, we escape this potential threat to the solar system. Because there are these different screening mechanisms, different gravity theories will sort of switch on and off at different scales. And as we've said, that makes them quite challenging to simulate. So in that nonlinear regime, let's talk a little bit again about kind of tools and computational tools. We're now in a regime where density perturbations are much larger than 1, so we can't expand our Einstein field equations in small quantities anymore. And so we do resort to computational techniques, and these simulations will have basically a field of dark matter particles that will be laid down according to some initial conditions and moved forward in a series of time steps. And according to your modified gravity model, you will have a sort of modified force law between two particles in that simulation. And that includes a description of how this screening effects kick in. These codes are really expensive to create and run. I mean, both in terms of person power, developing them can take a few years, and then, computing resources. These are things that may have to run on sort of local or even sort of national scale clusters. I'll write some names down here. Again, these might be things you come across in the literature. So these are some of the biggest codes that have been modified to run in modified gravity. They're not just lambda CDM codes. So eCosmog, MG-Gadget, AREPO-MG, these are some of the biggest ones. MG-GLAM is a fully relativistic code. There's some smaller, more model-specific codes here. And I tacked on HiCola at the end because that is the code that my group develops. And so I couldn't resist just putting in one really selfish slide here where I show you one of our simulations. So this is a snapshot through one of our simulations, one of our density fields in a Horndeski model of gravity. This is actually in a particular Galilean style model. But the point is we can run the simulations of these scales in any of those Horndeski theories. Okay, I'm very nearly at the end of my time. There is one more thing I promised to tell you, which is I promised to tell you what happened to DGP, which was the gravity theory we met yesterday. That was the brain world model. And I said that the sort of real excitement about DGP gravity was that it had this self-accelerating solution. So it had these two branches of the theory, depending on whether epsilon was positive or negative. But if epsilon was positive at late times, the Hubble value tended to a constant. So it self-accelerated. So where DGP kind of fell apart was when people really studied the dynamics of perturbations in this theory. So what you need to study in DGP is the dynamics of the brane bending mode, right? The flexion of that four-dimensional brane. And that gives you a degree of freedom we call pi that ends up acting like a scalar field. And that's why yesterday someone asked, why did I have DGP gravity in my table of Horndeski theories? It's because it ends up looking like a scalar field model. And so you expand the action for this scalar field brain bending mode. Again, I'm not sort of deriving this. You'll find lots of terms in your action, in your Lagrangian, that look like this. Okay, so there's sort of various derivatives acting on pi. And in particular, this is the term that's going to cause us problems. Then you do perturbation theory, right? So you allow pi to have some background value and some fluctuations. And you plug that in, you work out the kinetic term for these perturbations delta pi. And the coefficient of that term, the actual value of that coefficient, depends on the cosmological background expansion rate. So if you evaluate it on the self-accelerating branch of DGP, it shows up with the wrong sign. Okay, here it is just isolating that term. So this is like a kinetic term, but it's positive here. Whereas if you look at something like this was quintessence we had yesterday, it's got the opposite sign to the kind of standard canonical scalar field kinetic term. So ultimately, DGP, at least the self-accelerating branch, ends up having a ghost and therefore is unstable and is not allowed. You can still study the other branch of the theory where epsilon is -1. That's okay. That branch is stable and healthy, but that branch doesn't self-accelerate. So then you have to put in a cosmological constant by hand. And so it's just like a less exciting, less attractive theory. Okay, I have got to the end of what I hoped to tell you about modified gravity and dark energy. So I hope it's been a useful tour. I don't do very lengthy conclusions, but briefly, what have we done? We've met some of the most significant modified gravity theories that have shaped the field. And hopefully I've given you a flavor of how they affect the growth of dark matter perturbations on large scales, gravitational lensing, as well as things like the CMB and those other observables like the cross correlation. And we saw what the current bounds were on those theories. And we didn't actually comment on it at the time, but the tightest bounds on those two parameters, CB and CM, is actually currently coming from the electromagnetic side, so from the galaxy surveys. Now, there are parts of these theories that gravitational waves can probe. Like you will never measure alpha t, the speed of propagation, with a galaxy survey. So really what we need to do to sort of constrain this space of possibilities is really a sort of synoptic approach that uses both gravitational waves and galaxy surveys. Okay. And I think that's what I've said already, that large-scale structure is currently the best constraints, but that is a regime that faces a lot of challenges in the nonlinear modeling. And of course, the hope here long term is if we, let's say we completely constrain Horndeski gravity and that's ruled out, that's good, that's useful. That tells us then that we should look for other new theoretical ideas instead to play the role of dark energy in our universe. Okay, sorry for running a little bit long on this side of the break, but I will happily take questions.
Thank you. Thank you very much, Tessa. That was wonderful. Maybe we have time for one quick question. I want to make sure we have enough time for lunch. We don't run too far over, but one or two maybe.
Hello. Thank you so much for the talk. I have a couple of questions, but I'm only going to ask one.
Okay.
Could you go to the slide where you're talking about the simulations that include modified gravity?
Yes.
Um,
I'll go backwards. Ooh. These
so
ones?
yeah, yeah. So from my understanding of how they like do this is I'm sure you can compute like a power spectrum of like modified gravity, and then from there you like feed this power spectrum to the n-body simulation, and that's how you like perform, I guess, like you tackle the nonlinear like regime of the universe. Is that correct? Or
So you definitely can compute a power spectrum of in your modified gravity theory in linear theory. You don't actually need to do that. in some sense that you run the simulation, as long as you set the initial conditions up right, it
Mhm.
will give you predictions for the full range of structures. Full range of scales. So it will predict the linear parts of the power spectrum, but also the non-linear parts. But then you can do a good check, right? It should be a sort of sensible validation exercise that what comes out of your simulation should match the power spectrum that you could compute analytically in the linear regime on large scales.
Oh, that makes sense. All right, thank you.
Thanks.
Very good. And if we had one quick question in the back here, and then I think we'll break for lunch.
Hello. Thank you for your talk. I have a question. When you have an object that crosses over from an unscreened region to a screen region, does that object maintain information about modified gravity from that crossover? And if so, how can you distinguish that between other effects like uncertainties in baryonic physics or cosmological parameters?
Ooh, that's a really good question. Um, because a lot of these screening mechanisms, the sort of papers that are written and the studies that are done, are often done in static or sort of quasi-static, so very slowly evolving scenarios. And actually, we believe that screening often breaks in a highly dynamical scenario. So if you literally, the situation it sounds like you're describing, where you sort of, I don't know, could throw some object across some sort of screening barrier, there would definitely be like time dependent effects. It wouldn't just immediately sort of become screened and not have any information of the modified gravity. So there would be some sort of settling down period in that situation. I've now forgotten if there was a second part of your question. Sorry.
I was just wondering if that can be distinguished between other things like uncertainties in baryonic physics or just measurements in general.
Great. Yes, good question. Because you're absolutely right that on those sort of quasi nonlinear to nonlinear scales where I say screening kicks in are the scales where baryonic physics becomes super important. And that is a big problem that we worry about. And that's really, to study that requires lots of these simulations that are very expensive to make. So the current belief is that there probably is some degeneracy between baryons and modified gravity, but it's not perfect. There have been studies showing that they do just do slightly different things if you study the right quantities, and so hopefully you could still disentangle them.
Wonderful. Thank you so much, Tessa. Let's give her one more round of applause.
Thank you all for listening, and I hope you have a great rest of your week. And yes, I will pick up those questions on Slack going forward.
Perfect.
Thanks.
All right. Let's plan to be back here around 2, but let's maybe a little bit of wiggle room there. I know people want to get a good lunch, so 2-ish, but couple minutes late, it's probably fine.